Today I'm going to be showing you an approach to controller tuning that is finding a good value for the different gains in your controller that is a little bit more defined and gives you a little bit more insight into what are the effects of changing the controller gain. This approach doesn't have anything new that you haven't seen before. It just combines and puts together things that we've learned before in this class in different contexts, and we're going to be applying it to the application of tuning a controller. So to start out with, I'm going to assume that you have a feedback control system that looks like the standard feedback control block diagram that we've seen previously. We have an input command, we have a controller, and the controller is going into the plant, that is the system we're trying to control, and then the output is coming back through a sensor and the sensor value is being subtracted from the input. Now I'm going to walk you through how this tuning method works by just giving you a concrete example. So let's start out by assuming that my sensor transfer function is equal to 1. This means that the output of the plant, when read by the sensor, is reported exactly correctly. We're assuming that the sensor is a very good sensor. Also, in this example, I'm going to assume that the plant is actually a motor. So we can use the transfer function that we found previously for a motor. The transfer function that I want to use is the transfer function that takes as the input voltage or applied voltage, so I'll label this arrow as applied voltage, and the output is the rotational speed of the motor. So this feedback control example is an example of speed control for a motor. The overall input to the whole system will be a commanded speed. The sensor will be reporting speed so that these two arrows are the same units as is always necessary. And then this arrow, which will be the difference between the two speeds, will be the error. Now for this example, I'm going to assume that the controller is just a proportional controller. That means that the controller is going to take the error, multiply it by a constant, which we'll call Kp to represent that it is a proportional gain, and in that way calculate the voltage input to the motor. So let's find the transfer function for each of these blocks. We already know that the sensor block is 1 and the controller block is Kp. Let's take a look at what the plant, the motor block, is. We've found this previously, so I'm just going to show you what it is. Here's the transfer function for our motor. Since we now have the value of the block for each one of the blocks in my feedback control block diagram, we can now find the transfer function of this entire system by doing our block diagram reduction method. So in the numerator, I will have the whole forward loop, which is Kp times the motor, and then in the denominator I'll have 1 plus the controller times the plant times the sensor. So let's find this whole overall transfer function, which I'll just call Tf. Now, I want to simplify this a little bit by getting rid of the denominators in both my numerator and my denominator. So the way I'll do this is I'll multiply the numerator and the denominator by this whole term that shows up in the denominator. So I'm left with just k times kp in the numerator. And in the denominator, I have this. Now that I have the complete transfer function, I can use an approach that we've seen used several times previously in this class. What I'm going to do is I'm going to compare this transfer function to the standard form of the second order transfer function. And the standard form of the transfer function, I'll call that TFS for standard, looks like this. We have some kind of a gain, and then omega n squared in the numerator, if we can match our transfer function to this standard form of the transfer function, we can find equations for the natural frequency and for zeta and for the gain. Those three things are all we need to define all of the important characteristics of the step response of this system, including things like the steady state error, the amount of overshoot, the rise time, the peak time. All of those important characteristics will be defined by these three parameters, omega n, zeta, and gain. Notice that in our transfer function, one of the variables that we have is Kp, the gain of the proportional controller. All of the other variables are parameters of my actual plant. These things are things like the motor constant, the inertia of the motor terminal resistance, the motor inductance. These are all things that are characteristic of our plant, the thing we're trying to control. So if I go and plug in numbers for each of these things, then the only variable left is Kp, my controller gain. I can then solve for Kp by determining what I want these different characteristics to be. In other words, I could set what I want the steady state error to be, or I could set what I want the overshoot or the rise time to be, and I could back calculate the value of Kp that will give me that value. So I'm going to show you how we do that with this example. What I need to do is I need to make my transfer function match this standard form. The first way that my transfer function does not match the standard form is the coefficient in front of s squared. I have j times l, and the standard form is 1. So I'm going to start by pulling j times l out front. Next, the standard form has omega n squared in the numerator and also as this constant. In mine, the constant in the denominator does not match the numerator. I need to pull another constant out front that will get this numerator to match the constant in the denominator. I know that one way I can do that is by taking the thing that's already in the numerator and put it in the numerator out front, then take the thing that I want to be in the numerator, flip it upside down or take the inverse and bring it out front. So I'm going to take this term and bring it out front, but I'll flip it over first. And then what I'll be left with in the numerator is this term. And the denominator will be the same. Since this term is long and complicated, I'm going to first simplify this up a little bit. This j times l cancels out here, and then I can merge these things that are left into one. And the rest of this is the same. My equation now matches the standard form. I'm going to match each of these parameters with the terms in my equation to find values for each of these important parameters, omega n, zeta, and the gain. So the gain in my equation is this term out front. Omega n is then the square root of the term that appears in the numerator and that it appears as the constant. And 2 times zeta times omega n is this term right here in front of the s. How can I use knowledge of each of these things to find a value for Kp? If you remember from the very beginning of class, each of these things zeta, omega n, and the gain have something to do with different characteristics of the step response. The gain is the value that is multiplied by the step input that determines the steady state value of the system. So if I apply a step input of 1, that value 1 will be multiplied by this term, and that will be the steady state value of the step response. Since I have a control system, I would like the steady state value of the system to be equal to my input. Any difference between the steady state value and my input value will be steady state error. So steady state error here is equal to 1 minus the gain. Now, steady state error is typically always positive, and I can't be sure that the gain is going to be less than 1, so I'm going to actually take the absolute value of this, and that will be my steady state error. These equations also determine the overshoot. The overshoot, if you recall from way back in the first part of class, has this equation. Since omega n has as the only variable in it Kp, all of the other variables are determined from the system, and 2 zeta omega n has no variables, the only thing that zeta depends upon is the value of Kp. We can set Kp to get us a desired value of overshoot. So if we want to have 0 overshoot, we can set Kp in such a way that zeta is 1 or greater than 1. We can also determine the speed of the response. For example, from the peak time. The peak time we learned a long time ago is pi over omega n times the square root of 1 minus zeta squared. We can plug in these equations that we have for omega n and zeta, and we can solve for the value of Kp to give us a particular peak time. I'm now going to show you how we can do this by putting these equations into Excel. We know that we could use MATLAB's built-in functions to simulate the step response of our system, but there's a way that we can just use Excel to calculate the key parameters, omega n, zeta, the gain, and then use those parameters to get things like the steady state error, the overshoot, and a time parameter like the peak time or the rise time. This is particularly useful because it allows you to test many different values for Kp to get a feel for what the effect is without running simulations over and over and over again to find what the effect is of the values of your gains. To do this, I'm going to start by putting in values for each of my system constants. These are the parameters of the motor that I would get from the motor datasheet: the damping, the resistance, the motor constant, the inertia, and the inductance. I'm going to use values that we've gotten previously by looking at an actual motor datasheet. The damping I'm just going to estimate because the damping coefficient is generally not given in a motor datasheet. Next, I'm going to create an entire column that I can use to enter values for Kp. Each different value I enter for Kp will give me a different value for the gain of the system, for the natural frequency of the system, and the damping ratio, zeta. Each of these things will in turn give me different values for the steady state error, the overshoot, and a time like the peak time. I'm then going to enter the equations that we found previously earlier in this video for each of these values. So for example, the gain, we found that to be equal to K times Kp in the numerator divided by B times R plus K squared plus K times Kp in the denominator. Now for each of these cells, I want all of the cells to stay the same except for Kp, because Kp is the one thing that I'm going to be changing. So I'm going to put a dollar sign in front of all of the cells and numbers that are not Kp. And I'll also enter a value for Kp here. Now, I want to simulate what these things will be for different values of Kp. So I'm going to make each value be the previous value plus, say, 0.1. Then I can drag these values down and see how the gain is different for different values of Kp. I can do the same thing for omega n and zeta. Here I'm just going to enter the equation that we just found for omega n. Omega n is going to be different for different values of Kp, so I want this one also to be an entire column. I'm going to freeze each of the cells once again that is not Kp. These are all of the constants. If I then drag it down, I can see how the natural frequency of my system will be different for different values of Kp. I can do the same thing for zeta, and I'm going to do zeta by using my equation for 2 zeta omega n and then dividing it by 2 times omega n. Now, in order to drag this equation down, I need to freeze all of the cells that are in the column B, since those are constants. But I don't want to freeze the cell that is omega n, because omega n changes for each value of Kp. Already we can see a trend that we can imagine how it will affect the step response. When Kp is 0.1, zeta is relatively high, 0.86. The system is still underdamped because zeta is less than 1, but 0.86 is relatively good for a value of zeta. The oscillations won't be too bad. As Kp increases, we can see that zeta decreases. Let's take a look at the effect of Kp on these different important parameters: steady state error, overshoot, and peak time. We found that steady state error is going to be 1 minus gain, since our step input is going to be 1 and the gain tells us what the steady state value is. So I'm going to set ESS be equal to the absolute value of 1 minus the gain. Here we can see the effect of increasing Kp on steady state error. As Kp becomes larger, the steady state error becomes smaller. If I had some precision requirement for my system, for example, the speed of the motor must match to within some limit, that would help me determine what Kp would have to be. Another effect that we can see here is that there's a trade-off occurring. As Kp becomes larger, zeta becomes smaller. This should affect our overshoot. However, as Kp increases, steady state error also becomes smaller. That means that as we increase Kp, the system becomes more accurate, but it also becomes more unstable. Let's look specifically at the value of overshoot. I'm just going to put in the equation that we have for overshoot. If I would multiply this value by 100, we would get overshoot as a percentage. As it is, this overshoot, since our input is a value of 1, is telling me how much overshoot there is. For example, if we set Kp to be equal to 0.1, and our command is 1, remember this is units of speed, so this might be 1 RPM, for example. The speed of the motor will overshoot 1 RPM by 0.004 RPM if we set Kp to be equal to 0.1. That's a pretty small overshoot. However, the steady state error is pretty big here. When we command 1 RPM, the steady state error will be off by 0.77 roughly RPM. That's a major steady state error. As we increase Kp, the overshoot becomes bigger, while the steady state error becomes smaller. Lastly, let's take a look at the effect of increasing Kp on speed. The peak time equation is pi divided by omega n times the square root of 1 minus zeta squared. The peak time here is really small, no matter what we set Kp to be. Very likely, speed is not an important design consideration in this speed control application. we're probably going to be more concerned with the balance between steady state error and overshoot. Now, note that this whole simulation is just for KP, that is, just a proportional controller. At this point, we'll decide whether any of these values of KP gives us a desirable output, that is, a good balance between the steady state error and the overshoot. If we cannot find a good value of KP that achieves a good balance, we can go back and assume that our controller is not a proportional controller, but is maybe a PI, proportional and integral controller, or PD, proportional and derivative controller, or complete PID. We would then rederive our equations and find the new equations for omega n and zeta and plug in different values for the gains there. But the procedure would be the same. This approach to controller tuning can help you to find approximately good gains for your controller without having to actually simulate the step response for many different values of controller gains. You can also do this without even having MATLAB software. And using this approach can give you a good intuitive feel for what are the effects of changing different gains on different important parameters of the step response, like steady state error and overshoot. It's often good to do an analysis like this before you start to actually try to tune the gains on your physical system. This way you can start out already having some idea of what changing different gains will do to your system, and also what is a reasonable practical range for the different gains.